So welcome to Algorithm Seminar. Today we're happy to have Dmitrii to give a talk here. He's a last year PhD student at Indiana University, advised by Professor Grigory Yaroslavtsev. His main research area is continuous optimization, in particular in federated learning settings. He's also broadly interested in the theoretical foundations of machine learning and approximation algorithms. Previously, he interned at Meta, working on a grid descent-based algorithm for balanced graph partitioning, and Amazon working on graph convolutional networks, federated learning, and few-shot learning. Please welcome our speaker.
Yeah, thank you for introduction. So yeah, as you might have guessed from the introduction, this is not my usual area. So here we'll talk about hierarchical clustering, which is a bit of a side project in the sense for me. So this project with Danny Weinstein. So he is also here. And thank you again for inviting me here. And so yeah, let's start. Yeah, so our goal is to build a hierarchical clustering tree, which you're probably familiar with. And it has a lot of applications, including biology, statistics, different classification tasks, and more importantly, I guess, visualization. So for hierarchical clustering, there are multiple algorithms. You probably know about agglomerative clustering, but this algorithm requires pairwise distance and similarities. There are top-down approaches, which are focusing on performing the top-level cut, so performing the cut in the root. Yeah, there's various heuristics. They usually require pairwise distance and similarities, and some other approach require that your data is Euclidean vectors, so that you can do some like manipulation NRD on these vectors. For example, random cut. So the problem is that these distance similarities might be not available, or in some cases, the problem of finding a good tree might be intractable. So instead, we consider the following type of inputs, so which we call odd one out constraints. So given 3 items, so for example, here we have 3 images, we ask someone, either some program or, for example, a user, if you do some crowdsourcing, to determine which one is different from other 2. And in this case, for example, well, dog is clearly different from cat, so it will be an outlier. And so we will write it like this, so in this form. So if you want to separate B from A and C, then we write AC like bar B. So we'll use notation later. So how do we use these constraints? Okay, sorry. So first, another application aside from crowdsourcing are phylogenetic trees. So for when you analyze organism, you can measure some similarity between organisms or distance, but the problem is to reconstruct the tree given this data. And as I understand the paper which introduced this approach, the idea of using this odd one out constraint, it produces more reliable result. In the sense that, well, you can more reliably set who branched first and build a character tree this way. Oh, by the way, if you have any questions, then please stop me. Like, my presentation should be relatively short. I think maybe half an hour, maybe 40 minutes. But yeah, because I decided not to take all the time for no reason. So yeah, how do we use this constraint? For example, if you're given these 2 constraints, then we can say that some trees are possible. For example, these 2 trees are allowed. Because, for example, first tree satisfies first constraint, because after you remove this doggy, then it looks exactly like a constraint. The same for the second tree. And on the other hand, which is more importantly, it doesn't allow some trees. For example, if you look at the second tree, at the last tree, then if you remove doggy, then well, the remaining tree doesn't look like the constraint. So it violates a constraint. Another question is, like, how many constraints you need before you can identify the tree? So trivial upper bound is that if you have orientations of all your triplets, by orientations I mean like which constraints they have. Like if you have all the data for all your triplets, then of course you can recover the tree. And on the other hand, of course, you need to see every element at least once. So these bounds are trivial, but if you look at not real bounds, the situation is not that good. The previous work shows that you need the matching number of queries, like basically trivial number of queries before you can recover the tree. And you can do better if you have adaptive queries. So by adaptive, I mean that you can select for which triples you want to know the orientation. And non-adaptive means that the triples are sampled randomly and you just get the answer for them. And yeah, for non-adaptive queries, the situation is kind of bad. So instead, we decided, okay, let's not try to recover the correct tree. Let's try to recover almost correct tree. And for example, assume this is the correct ground truth tree. It's the only tree which satisfies these 4 constraints. There is no other tree which satisfies this constraint. And in particular, it means that this tree is not correct. But this tree is not bad in the sense that, yes, it violates the first constraint, but it satisfies all other constraints. And here we say that error rate is 1/4. And basically, our goal will be to recover almost correct trees. Any questions so far? Okay. So in our settings, we assume that we are given n elements, and our input is m randomly sampled constraints. Our goal will be to determine m. So we want to build a hierarchical tree, which is the largest fraction of all constraints. So we know m constraints, and there is overall n choose 3 constraints, and we are interested in the performance on all constraints. So our goal to have error rate at most epsilon. And also there is condition that the algorithm must succeed with probability at least 1 minus delta. So the question is how many samples we need. So how large our input size should be. And for answer this question, if you look at the previous step, our goal, then it looks a lot like PAC Learning. And this is exactly what we will be using. And our result shows this sample complexity. So basically, this number of samples you need before you can recover to have error rate at most epsilon. And we ignore this polylog on epsilon delta, and we use this notation. So this tilde notation, it doesn't ignore any dependence on n, but it ignores polylogarithmic dependence on epsilon delta. And just to clarify some doubts, this polylog is very good. So there are no log to this power of 7, etc. So let's talk about this result a bit. So when we first started working on this project, we kind of expected n log n result. And basically, this is what you would expect using some probabilistic method. So basically, the idea is that how many hierarchical tree exists? Well, it's 2 to the theta n log n. And basically, if you select your constraints wisely, you can expect that the number of remaining trees decreases by a constant factor. And this is why you expect n log n samples. But as we show, our result is actually less, which is kind of surprising. And what's also cool about this result is that it has linear dependence on n, again, if you ignore epsilon delta, which matches the lower bound we had before. Basically matches trivial lower bound. And also, we have some other generalizations of this result, which I outline in the end of the talk. So, like I promised, we'll talk about PAC Learning. So you may be familiar with it, but let me just repeat just in case. So we have some set of inputs x and set of labels y. And we have a label for each input. So we use this function h star, which maps inputs to labels. And our goal is to find this function. But it can't be just arbitrary function. So we have some set h, which you call hypothesis space, which is the set of functions which you consider. So we don't even think about functions outside the set. And there can be 2 cases. First case, this h star is in our hypothesis space, which you call realizable case. And another case, well, it's when it's not the hypothesis space. To give some intuition here, for example, here in our case, realizable case corresponds to situation, well, the constraints don't contradict each other. meaning that there is some tree which satisfies all constraints. And agnostic case means that the constraints are contradictory. There is no tree which satisfies the constraints. And the goal of PAC learning is that given your training set, we want to find some representative from hypothesis space which has error by at most epsilon greater than h star. And there is error probability thing, which doesn't matter in this talk. So it's honestly the most dense slide in today's talk. So any questions about that? Because it will be kind of important.
I just wanted to make sure, did you mention what the error is exactly?
Yeah, I didn't mention. Sorry. So basically, this is error rate. So you have all possible triplets. And error is on which fraction of triplet, in particular, if you didn't see, yeah, you get the correct result, incorrect result. Yeah,
Great.
yeah, good question. Thank you. Any more questions? So this is for classification problems. Now, I think one of maybe the main ideas in our paper is actually to think about problem as a classification problem. So our inputs are triplets. So we have 3 points ABC, and it can have 3 possible labels, depending on which element is an outlier. So which element is odd one out. So basically, the size of our label set is 3. And recall I mentioned that our hypothesis space doesn't allow all possible labels. It only allows labels which are induced by some correct tree. So for example, consider 4 labels, A, B, C, D. There are 4 different triplets on these labels. And for example, if you consider these labelings, then these labelings are allowed because this tree satisfies all the constraints. So yeah, you don't have to check this, just trust me. And on the other hand, this for labeling there is no tree which satisfies all these labels, all these constraints. And yeah, it's not in our hypothesis space. So what's good about PAC learning? The good thing is that it basically answers all our questions. First, it says what the algorithm is. The algorithm is empirical risk minimizer. And in the realizable case, it just means that we need to find a tree which satisfies all known constraints. And there are already algorithms that do this, but we will discuss this in more detail later because it matters for like other ideas. And for agnostic case, we want to find the tree which satisfies the largest number of known constraints. So for example, here, like this is a realizable case, you can build this tree which, well, satisfies all constraints, and this is exactly what we want to do. And this is example of contradictory constraints. And again, we can build some tree which violates only one of the constraints, I believe. So, sorry, I messed up a bit. Okay. So another thing that PAC learning gives us is sample complexity. So it says exactly how many samples we need. So the answer is that it has linear dependence on certain dimension. In binary case, it's VC dimension, and in non-binary case is Natarajan dimension. So yeah, there is a chance that you know about VC dimension, but you probably didn't hear about Natarajan dimension. So I will try to explain what it is in the talk. And our key technical result is that for hierarchical clustering, the Natarajan dimension is exactly n-2. And there is a good explanation why it's n-2, because it's actually n-1 minus 1. And I will explain what's so special about n-1 later. So let's talk about VC dimension, just to recap. So assume we have our data set, and we sample some set S, for example, of 3 elements from the set. And let's consider all possible labelings on this set. So since it's a 2-label case, there are to the power of S labelings. And if all of these labelings are possible in our hypothesis space, then we say that the set is VC shattered. So using this definition, we can define VC dimension, which defines simply a cardinality of the largest VC shattered S. So for example, in this case, if S is the largest shattered set, then the VC dimension would be 3. And yeah, like I said, PAC Learning answers all our questions. In particular, it says how many samples you need for realizable and for agnostic case. Now we might want to generalize this for more than 2 labels, for example, for 3 labels. And the naive generalization is that, okay, let's look at all possible combinations of labels. Call the set VC shattered. So I use quotes because you will understand soon why. If all possible combinations are possible. But the problem is that doesn't work. So as far as I know, there is no theory using this notion. So instead of this naive VC dimension, there is this Natarajan dimension. And the idea is that, okay, let's again sample our set S. But now instead of all possible combinations of labels, for each element, we sample only 2 labels. So we choose 2 labels. For example, for B, we choose red and green, for C, red and blue, etc. And now we only consider combinations of these labels. So we have 2 to the S labelings. And for B, we only use reds and greens as we select. And now we say that the set is shattered if all of these labelings are possible. And what's important here is that these labels are chosen by the one who wants to shatter the set. So they're not adversarial. So they're selected so that like these are easy labels to satisfy. And if you think about this, it kind of makes sense why VC naive VC dimension doesn't work and this works. Because in naive VC dimension, basically, the more labels you have, the harder it is to shatter, which kind of doesn't make sense because, well, you have more options. But here you always have 2 options, and you can select them from the largest set of labels. So Natarajan dimension is just, again, the cardinality of largest shattered set. Yeah, clearly it's larger than VC dimension because it needs only to consider 2 to the S labeling instead of Y to the S labelings. And the result is the same as for VC dimension. Any questions about Natarajan dimension? So basically what's important, for example, in our case, we have 3 labels for every triplet, and we always choose only 2 labels. So let's first lower bound this. This should be easy. And basically the lower bound is at least n minus 2. And the idea is just to consider like n minus 2 triplets which share 2 elements. And so to recall the notation, we use this notation AB bar C to denote the case when C is an outlier. And this is how we want to partition them. So for any choice of labels, we can build the following tree, where the right tree is the elements which should be separated from A1 and A2. This element should be the ones which together with A2 are separated from A1. And this one, the one who together with A1 separates with A2. Yeah, sorry, it was a bit messy, but does it make sense? So basically, whatever the orientation we select for AI, it falls into one of these 3, and we just put this into this 3 arbitrarily. And after that, it just clearly satisfies the constraint. Any questions? Oh, so now let's look for upper bound. So let's consider these triplets and these labelings of these triplets. So we consider the top level cut in the tree. So we want to make the top cut. And now what we want to separate some vertices from another vertices. And first we notice that we can't separate A from B because it violates first constraint. We also can't separate A from C because of the second constraint, and A from D because of the last constraint. It means that we can't separate A from anyone, and it means that we can't perform the top cut, and the constraints are contradictory. And what we show that, in fact, there is no such set of n-1 triplet which we can label arbitrarily. So we can always select an irritation which leads to a contradiction. So before that, like describing an idea, let's talk about how we actually build a tree. So assume this is our constraints. Now let's look at the like top elements, bottom elements in our constraints, and let's create an edge between them. So if you look at the resulting graph, then in this case it looks like this. And what's important here is that if you want to perform the top split, we can't cut any edge. So basically, as I described in the previous slide, if we, for example, cut edge between A and B, then we violate these two constraints. If we cut between A and C, that violate these constraints, etc. And basically, well, we just need to not cut any edge, and it just means that we want to separate D from everyone else. So our top split looks like this. Now, every constraint containing D is satisfied, so the remaining constraint is ABC. Again, it creates only one edge. It produces the following graph. And again, we just need to cut C from everyone else, which leads to the following tree, which is just this. So any questions about this part? Because it's probably the most important thing to understand.
I didn't get why. How is this tree building related to the other one? Is it for you're trying to have the construct the upper bound, or?
So yeah, we want to construct an upper bound on Natarajan dimension. It means that we want to get a contradiction. So yeah, I will go to this. Yeah, sorry, I'm speaking a bit out of order, but yeah, it will be used a bit later. So here I just want to introduce this idea of connectivity, that we use connectivity to determine if there is contradiction or not.
Oh, I see. You wanted to see. Okay, sounds good.
Yeah, sorry, I understand that it's a bit out of order, but yeah, it's too late to change that. Sorry. Yeah, any more questions? Cool. So our algorithm is top-down approach. We build sets from top to bottom, and now we want to split some set of elements S. So we build connected components, as I shown on the previous slide. Well, we split S according to the connected components, and if S connected, then we just report that the constraints are contradictory. So, well, if the constraints are indeed contradictory, then algorithm evidently fails at some point. But if they are not contradictory, we can prove that it succeeds. So it's not hard to recover the proof from the intuition in the previous slide. So basically, as long as you immediately don't violate anything, you are fine. And so why it's support for Natarajan shattering? So this kind of gives us an idea how to build a contradictory irritation. For example, if you have a graph like this, which is connected, it means that these irritations of our constraints are contradictory. And it also gives an idea why n-1 constraints are required. Because n-1 edges is like the minimum number of edges which are required to connect the entire graph. And this is basically the whole intuition where n-1 comes from. So, yeah, like main idea is that if you have n-1 triplets, then we can always select, we can always choose constraints such that there is a set which is connected by the edges produced by the constraints. So the good thing is that we know how to define such set. So basically, each set with the following properties. First, it has at least S-1 triplets. And on the other hand, it should be the smallest such set for some technical reasons. And clearly, if you have n- triplets, then the whole set satisfies the first condition. So such set definitely exists. As for example, if you consider triplets ABD, ADB, ABC, and ACD on 4 points, then this set has 3 triplets, and if it's the smallest one, then it's a critical set. And basically what we are saying that this critical set will lead to a contradiction. So the idea is that we look at the set S, we ignore everything else. So we select the irritations of the constraints of the triples, we generate the maximum forest. Maximum in terms of number of edges. So now, if this tree is maximum, the set is connected and we are done. But if it's not connected, there is some unused triplet. Let's call it ABC in this case. And the idea it's unused in the sense that, well, it has some constraint, some orientation. It produces some edge, but we don't use this edge for connectivity. So now the idea is just to use it for something, to connect, to increase our forest. So for example, in this case, yeah, I spare you details, but basically you can change two constraints. First, this constraint ABC and another constraint X, Y, Z, where Z is another tree in the forest. And basically you connect two trees. So this is the simplest case when you can just immediately reorient two constraints to connect two trees. And this increases your forest, it leads to a contradiction, but in general, the situation is a bit more complicated. So it's some case analysis, which I skip. So any questions about this? So the proof itself is, yeah, it's involved with a lot of case analysis, but this is the idea. So we build select constraints, select orientations, which produce the maximum forest, and then we show that it's in fact not maximum by changing some constraints. So this result, which I showed before, it assumes that we can select any constraint for our triplet, meaning we have three options for every triplet. But recall that Natarajan dimension allows only two labels. And the idea is just to change orientation of the constraints which violate this requirement. So for example, consider this case when we build a connected, we connect our set using some constraints, but this constraint ABC is not oriented as required. So for example, Natarajan shattering required only edge AC or HBC, but we instead select AB. And the idea is that, well, this edge, it connects two connects components. So we just should reconnect them. And basically in this case, if A and C are in the same connected component, we just use HBC instead of HAB. And the connectivity remains. So that's it about main part. Any questions? So what we did, we proved that the untouched dimension is exactly n-2, because we have this lower bound for n-2, and right now we show that Natarajan dimension is less than n-1, because for n-1 we can get contradiction. Any questions? Yeah, so now let's talk about some generalizations. So first, we might consider non-binary trees. For example, in this case, you might not be able to decide who is odd one out, who is different from others two. And for example, you can consider this kind of constraints, where everyone is separated simultaneously. And our result is exactly the same. So the Natarajan dimension doesn't change, everything doesn't change. So the idea is the same, is we use connectivity. So first we generate edges as before for the constraints of odd one constraints. But there is something with these constraints where like everyone is separated simultaneously. So for example, in this situation, if A and B are already connected by other edges, and we have this constraint ABC, like A bar, B bar, C bar, then we can connect A to C. And the idea is that what the meaning of these constraints A bar, B bar, C? The meaning is that they should be either separated at this level right now, or they shouldn't be separated. And if they are connected, then of course, if A and B are connected, then they shouldn't be separated. And well, C also shouldn't be separated, so we may as well connect them. And we can repeat adding these edges until this process converges. And on the other hand, if A and B were not connected, A and C and CB also were not connected, then we couldn't do anything with this constraint. And the algorithm is the same as before. So we build some connected components using this approach and just split these connected components. And the proof idea is again to use critical sets, which is the set with at least S-1 triplet. There are some problems with Natarajan dimension. because now we have one more option, but it's again some case analysis which we handle. Any questions about this, in particular about how we generate edges? So basically, the idea is that this constraint, it says that either everything should be separated simultaneously or should be not separated at this level. And if two of them are connected, then we as well can connect the third one, meaning that we can't separate them. Okay. For k-tuples are, we can consider constraints of k elements. For example, we can think about this tree as a constraint on 4 elements. So basically, the constraint is just a tree with k leaves. So notice that for k equals 3, it matches our previous definition for triplets. Yeah, it doesn't matter. And our result is that Natarajan dimension is between n minus k and n. So it means that for constant k, the dependence on n is linear, and the result is again the same. So now you might wonder, like, isn't it weird? Because this constraint gives us more information. So more information than just a triplet. But on the other hand, when we query, like when we want to get a result for new constraints, for new k-tuple constraints, we also require more information. So the proof idea is that the upper bound is that every k-tuple constraint, it has at least one triplet constraint. For example, if we look at this tree, we can ignore the doggy, and well, it's just a triplet constraint. And for lower bound, the idea is the same as for triplets. So we just fix k elements, and we just place other n minus k elements as we want. Any questions here? So now let's talk about non-realizable case. So again, Natarajan dimension answers all the questions. It says how to achieve minimum error rate. It says that you want to use empirical risk minimizer. Yeah, but there is a big problem here, is that it's not clear how to actually minimize the loss on the known triplets. So there is trivial of an approximation. Basically, you just do min cut at every level. And you, of course, have at most n levels. And it's close to lower bound. And in our experience, we also didn't get anything good with non-realizable case. For realizable case, our experience surprisingly well matched with theory. So basically, it's like exactly constant dependence compared to what we expect. But for non-realizable case, yeah, we tried some tweaks, but we couldn't do anything good. And finally, we consider align settings. Basically, we have a stream of triplets. And for each triplet, we want to predict the label. After the prediction, we know whether this prediction was correct, and we know the correct answer. And well, if the prediction was incorrect, that it's an error, and we want to minimize the number of errors. So for realizable case, we have n log n bound, and for non-realizable case, yeah, it's a bit more involved. I don't want to focus on that, so it's in the paper. Yeah. And in conclusion, so we have tight bounds for sample complexity. So basically, everything is tilde. So for sample complexity for tree learning, for binary and non-binary trees, for k-tuples for any constant k, for realizable, non-realizable case, for any combination of the above, also for online settings, and also, like as a free lunch from PAC Learning, we allow any distribution on triplets. Well, so there are some open questions. For example, what can be some natural assumptions on the efficient empirical risk minimizer in non-realizable case? Well, like I mentioned, in our experiments, it didn't work out well, but maybe for some cases it can work better. We don't know. And maybe if you use adaptive queries, not just random distribution on triplets, we also can do something better. So, thank you.